Okay, so for today's class, we're going to be looking at kind of the opposite side of hypothesis testing. Everything we've done so far has been focused on the null hypothesis and um, setting up the null hypothesis with HO and the mean for the null hypothesis, and then running our inferential test and seeing if we have evidence to reject the null. And in the background has always been the alternate hypothesis, what we think might be going on. But as we know, we we don't work to prove the alternate hypothesis. We work to find evidence that would suggest that the null hypothesis is not true, right? So it's like you don't go out trying to prove if all dogs have four legs. You don't go out trying to prove the alternate hypothesis. You go looking for do dogs have three legs, right? So, and we're going to focus today on two types of error. Type 1 error is what we have focused on for the longest time, and that's type 1 error. That's rejecting the null hypothesis when in fact the null hypothesis is true. And as the little cartoon says, according to my p-value, I rejected the null. The null hypothesis is true, and these two creatures are different. Well, they're not different, they're the same. The null hypothesis is true. Then we're going to look at type 2 errors. That's where we fail. That's where the alternate hypothesis is true, and we fail to reject the null hypothesis. So according to my statistical power, these are the same. I didn't reject the null hypothesis, but I should have, because the alternate hypothesis is true. And therefore, what do I conclude? I conclude that there is no difference and the two creatures are the same. So we're going to focus heavily today on statistical power, which is looking at the alternate hypothesis and type 2 errors. Okay. Okay, so Statistics Canada has informed me that from the last census, the average age of Matchedash Township residents was 50 years with a population standard deviation of 15. Right? So that's status quo. Nothing's changed. But I've been seeing that there's been some housing development in the Matchedash area, and some younger families have moved into Matchedash, and I think that's brought down the average age of Matchedash residents. So my null hypothesis is mu equal to 50, and the alternate hypothesis is mu is less than 50, right? And we go about running our inferential test. In this case, and I'll be using examples of commonly used the inferential tests that we've looked at, focusing on the z-test for a single mean, and then later on for the t-test for two independent means. So this one's going to be the z-test for a single mean. I'm going to compare my sample mean to the null hypothesis mean of 50, and I know the population standard deviation is 15. Okay. Now, and in this case, we would be dealing with the null hypothesis, which in this case I have, that's the blue curve. So that's the population of individuals for the null hypothesis. Now, I'm going to also kind of like think, well, I got to have some idea of what is actually going on if the null hypothesis is true. And I'm kind of like suggesting the population has got younger. So, you know what, to kind of like assess my study, I'm going to go, well, if there's been a drop in terms of the average age from 50 down to, say, 47. So let's say a drop of 3 years in terms of the average age, from 50 to 47. That represents about a 6% drop in the average age, which to me that's a practical knowledge to me. That is getting younger, and that's to me, in practical terms, I believe that's a pretty important drop in age in terms of the average age. So I don't know what the alternate hypothesis actually mean is, but I'm going to say anything kind of like around, anything that's 3 is kind of like the cutoff. So if the average age is 3 years younger, that's important to me. If it's more, that's fine. So to design my study, it ends up becoming important. What is the effect size? How big a drop do I need to see in the average age for an alternate hypothesis mean to be of some practical utility to me? If it dropped like 2 months, in terms of the average age, that's not really that important. I don't consider that big enough a drop. Maybe an average drop of 1 year. No, gosh, that's just fluctuation from one census to the next. But in my case, I'm going to say, you know what, if there's a drop in terms of the average age from 50 down to 47, that's pretty important. I'm going to go with that. That's kind of like the minimum effect size in terms of anything less than 3 years, I'm not really that interested. Anything more than 3 years, that's great. But the cutoff is anything in terms of a drop of 3 or more years is important. And 3 years is kind of like my threshold. I'm going to go with 3 years. So I'm going to assume that for the alternate hypothesis, I'm going to go with it being 47 years, right? So that's kind of like, if that's kind of like my threshold. Okay, so that the red line represents what I think for the alternate hypothesis, a mean difference of a drop of 3 years. Okay, so now I've got something that I'm kind of working with, in terms of not just the null hypothesis, but the alternate hypothesis. Now, nothing has changed in terms of the running of my test. I still going to do what I want to do, but where the alternate hypothesis becomes important is in terms of, as the cartoon suggests, in terms of type 2 error. And what it really comes down to is if the alternate hypothesis is true, if I go through my inferential testing and rejecting the null hypothesis, if the alternate hypothesis is actually true, well, how often would I be rejecting the null for my inferential test? Because I wouldn't be working with the blue curve, I'd be working with the red curve. Now, I would base my inferential test and I'd report alpha less than 0.05. But in the background, I'm going, okay, well, this may be what's going on. My alpha may be 0.05, but the probability of me rejecting the null hypothesis is not founded upon the blue curve. It's actually founded upon the red curve. Okay. So I can run my inferential test just like we would do, and I could base it on the null hypothesis distribution, a population mean of 50, and I want to reject the null. So I do my z-test, and as long as my z observed is more extreme than my z-critical, I will reject the null. And we've gone through the z-test multiple times, so everyone should be familiar with it. In this case, my z observed is negative 1.667, which is more extreme than negative 1.645. So my z observed is in the critical region, and I reject the null hypothesis, alpha equal to 0.05, and I'm happy, right? So if the null hypothesis actually is true, the probability of me committing a type 1 error, rejecting the null when I shouldn't, is less than 0.05, right? And that's what the meaning of alpha is in inferential testing. I can use my z-critical and find and work it based on my m-critical, right? And figure, well, how much smaller does how much younger does the mean have to, in terms of the mean population age for my sample, how much lower than 50 does it need to be for me to reject the null? And that cutoff is 45.065. So, and I put that into my formula. I can figure out m-critical. I take my z-critical, negative 1.645, multiplied by the standard error, and add my null hypothesis mean. So m-critical is 45.065. As long as my sample mean is less than 45, I reject the null. And in our case, my sample mean was 45, and I did reject the null. Okay, this is what you would do. This is what you would report. Nothing will change, right? So I'd make these conclusions. But when I'm doing my research design, I got to think, okay, well, what does if the alternate hypothesis is actually, let's say, the mean is 47, if I go with that distribution and I use my mean m-critical of 45.065, that's not going to change. If I apply that 45.065 to the alternate hypothesis distribution for the distribution of sample means, how often would I reject the null? Right? If the true population is actually the mean of 47, I should be rejecting the null more than 5% of the time, founded upon the null hypothesis being true. Okay. So here's my distribution of sample means for my hypothetical estimate of the alternate hypothesis, a mean of 47. And the standard deviation here is 3, right? This is a distribution of sample means for the alternate hypothesis. I still use my m-critical because that's the m-critical I would use for my inferential test. But when I take that m-critical and put it on this curve here, this tells me if the alternate hypothesis is true, how often would I reject the null hypothesis? If the true population mean is not 50, but is 47. So kind of like the curve has kind of like slid down, right, from 50 down to 47. Meaning it goes from 5% as the curve slides down to much more than 5%. Okay. Now, if the alternate hypothesis is true and the true population mean is 47, and I'm look at that distribution of sample means and I apply, and I look at and I use my M critical from my inferential test, what percentage of the time or what proportion of sample means are less than 45.065 for this distribution, and what percent are greater? So in this case, my Z for beta is my M critical minus the mean for the alternate hypothesis, which is 47, all divided by my standard error of 3. So my Z is negative 0.645. I go to my standard normal curve and I look up, well, what proportion of sample means are less than 45.065? And that is from the table 0.2595. The proportion that are of means that are greater than 45.065 is 0.7405. That means that if the alternate hypothesis is true, if I run my study 100 times and go through the same procedures I did on this slide, I would reject the null. Out of 100 studies, I would reject the null roughly 26 times. 74% of the time, or 74 out of 100 studies, I would fail to reject the null hypothesis when I actually should, because the null hypothesis isn't true and I should be rejecting it because the alternate hypothesis is true and the mean truly is, and the mean because the mean's 47. Beta, which is a type 2 error, is failing to reject the null hypothesis when the alternate hypothesis is actually true. And in this case, if the alternate hypothesis is true and the mean were 47, if I ran my study 100 times, 74 times I would fail to reject the null hypothesis when in fact the alternate hypothesis is true and I should be rejecting the null. I don't reject it. That's an error. That's a type 2 error. The statistical power of my test is if I run my study 100 times, 26 times out of 100 I would correctly reject the null hypothesis. That's actually fairly pathetic, meaning that, really roughly a quarter of the time I run the study, I'm going to reject the null when I should, right? That's pretty small. And 74% of the time I would fail to reject. In this design of this study, I have very weak statistical power. So if I'm doing this study for a client and I got 25 subjects, that sample size is actually way too small. I'm even if the population mean is say 47, I'm not going to be more often than not rejecting the null hypothesis. I got lucky in my one study. I barely was able to reject the null. So I have very weak or poor statistical power. I got very fortunate in my study, but for other people running the study, replicating what I did, they're going to basically accuse me of something wrong with my data because 100 other people replicated my study and 74 of them failed to reject the null like I did. So this means that what we have to look at, the driver of this we'll get to in the next part of this lecture, is actually the sample size. This is just kind of like throwing both, this is why I kind of broke it into pieces. This is like throwing both curves together. Here's the blue, or the blue stuff here is for the null hypothesis, mu equal to 50. There's my alpha, my 0.05, which is my arbitrary cutoff, that if the null hypothesis were true, that's the probability of me rejecting the null rejecting the null hypothesis when I shouldn't, because I've rejected it and the null hypothesis is true. The other curve, and what's in red, is if the alternate hypothesis is actually true. In that case, my M critical doesn't change, but I'm applying and looking at the area under the curve, not for the null hypothesis curve. I'm looking at it from the alternate hypothesis curve. And rejecting the null, if the alternate hypothesis is true, goes from not 5%, but it goes to, in our case, 26%. So 26% of the time I would reject the null because the alternate is true, right? And the table below here kind of just breaks it down. So if the null hypothesis is true, alpha is the 5%. 5% of the time I would reject the null when I shouldn't, and 95% of the time I would fail to reject, and that's the right thing to do. Null hypothesis true? No, the alternate hypothesis is true. Correct rejection is 1 minus beta, and that's referred to as my statistical power. I've correctly rejected the null hypothesis. A type 2 error, when the null hypothesis is not true, is when I fail to reject the null, when in fact I should. Okay. Now, once again, the math here isn't very complicated, but wrapping your head around it can be challenging. This is not conceptually the easiest stuff. Okay. So I guess take a deep breath, maybe work through the slides again, maybe the video. Their practice question. So I got the average Canadian walks 3,000 steps per day. So for the null hypothesis, mu equals 3,000. Sigma, the population standard deviation, is 500. I sample 9 Festerton residents to see if Festerton residents walk fewer than 3,000 steps per day. My data is to the right, sample mean of 2,800. Okay, you can complete the inferential test. Just go through like you would normally do for a Z test. State H0 and H1. Calculate your M critical for a Z critical equal to negative 1.645, and complete the Z test, your inferential test, and state your conclusion. That's kind of like that's what you would normally do. Okay, I'll present the results on the next page. So if you want to just pause it here, you can also. The other piece of it is, assuming H1 is true, and say the population mean is 2,900, so there's actually a 100 steps drop between the null and the alternate, so 2,900 is the alternate hypothesis mean. Using your M critical, calculate beta and the power of your test, which is 1 minus beta. Pause the video and go through the exercise of doing this, and then on the next slide, the results are taken up. Okay, hopefully you were successfully able to complete it. You should have found an M critical of 22,725.83. Your Z observed was negative 1.20, so you would fail to reject the null hypothesis. Using your H1 mean of 2,900 and your M critical of 2,725.83, you can figure out Z for beta is negative 1.045. The power of your test is 0.148, which means that roughly if someone were to replicate this study 100 times, only 15 of those studies would you correctly reject the null hypothesis. And 85% of the time, or 85 out of 100 studies, you would commit a type 2 error, or beta. You would fail to reject the null hypothesis. And that is for this section. What we'll go on to the next section is we'll look at, well, how do I develop a proper sample size? How do I know what sample size to use? Clearly, in this case, a sample size of 9 is way too low. Well, how do I know that? Because what's the driver of this? One of the big drivers is the standard error. And what does the standard error equal? The population standard deviation over the square root of n. As n gets larger, the standard error gets smaller and smaller. And when the standard error gets smaller and smaller, I'm better able to detect differences between the null and alternate hypothesis.